Moving through the chapter, we'll now discuss carbon nucleophiles. We're going to start with a brief review of organometallic reagents. So just as a reminder from the previous sections, organometallic reagents will add irreversibly to the carbonyl group. So for example, if we have a ketone or an aldehyde and we treat them with an organolithium reagent, the organolithium reagent will add to the carbonyl carbon, producing a lithium alkoxide as an intermediate. This alkoxide can easily be protonated by water or a weak dilute acid to give either a secondary alcohol from an aldehyde or from a ketone, a tertiary alcohol. So if you need a little bit more review about how these work or how we make the organometallic reagents, the place to go is Chapter 12, Section 6. There are, however, other carbon nucleophiles that we need to talk about, so now we'll discuss cyanide and the product it makes with a carbonyl group, a cyanohydrin. So if we take something like an aldehyde, here benzaldehyde, and treat it with a solution containing cyanide ions, well, cyanide is a pretty good carbon nucleophile, so it's going to add to the carbonyl group just like an organometallic reagent would. Since the cyanide ion is much more stable than an organometallic reagent, this addition is reversible to produce an analogous alkoxide here. This thing can easily pick up a proton, and these reactions are usually done in a solution containing a combination of HCN, hydrogen cyanide, and cyanide salts. The book discusses this at length. It's basically a safety issue. Hydrogen cyanide is extremely dangerous. If this picks up a proton, then we protonate that alcohol and generate another cyanide ion. So this is catalytic in terms of acid, and the product here is known as a cyanohydrin. So if we were to name this, since it originated from benzaldehyde, we call it benzaldehyde cyanohydrin. There are some natural products that are cyanohydrins, so there's many natural things that generate cyanide for defense or safety in one way or another. Three of these substances are amygdalin, laetrile, and mandylenitrile esters. So this compound here is amygdalin. You can see the cyanohydrin that's had a sugar molecule kind of grafted onto it. Amygdalin is found in apricot pits and apple seeds. So when your parents or grandparents told you not to eat apple seeds because they contain cyanide, this is actually the form that the cyanide is in. When this is exposed to the acidic environment of someone's stomach, the acid can cause the cyanohydrin to reform and then fall apart, which generates HCN, which is fairly toxic. There's an interesting derivative of this. So if we cleave one of these sugars, we get this product here, which is called laetrile. So laetrile was actually sold as sort of a cure-all substance, I think it was back in the 70s. So this was basically a quack medication. If you took it, it would produce cyanide and kill all your cancers, cure your diseases. Of course, it didn't do that. Finally, if you go hiking in the woods of North Carolina in the spring or summer, you might happen upon one of these very large millipedes. These are sometimes known as cherry bugs. These insects, and some other insects like them, contain this compound here, which is an ester of mandylenitrile, which is the common name for the benzaldehyde cyanohydrin. This compound can also fall apart reversibly in the presence of a strong acid, and this is how the beetles and millipedes actually safely store cyanide, which they can release to ward off predators like birds and smaller mammals. So we'll come back to these compounds again in Chapter 20 when we'll actually use the nitrile group to make other functional groups like carboxylic acids and amines. Next, we're going to take a look at a very special carbon nucleophile that participates in what's known as a Wittig reaction. So the Wittig reaction starts with a ketone or an aldehyde, and we're going to add this carbon nucleophile to it. So this carbanion here is right next to a phosphorus atom which has a positive charge. The species is known as a Wittig reagent or an organophosphorus ylide. So an ylide is a generic name for any compound which has a positive and a negative charge on two adjacent atoms. So when these react together, what we're going to do is a pretty remarkable transformation. We're going to get an alkene here. So this is synthetically useful enough that it earned George Wittig the Nobel Prize in 1979. And the other product we get is triphenylphosphine oxide. So what George Wittig realized is the formation of this triphenylphosphine oxide was the driving force for this reaction, as the phosphorus-oxygen bond is exceptionally stable. So how does this reaction work? For such an unusual looking reaction, the mechanism is fairly straightforward. First, we have a cycloaddition between the Wittig reagent and the carbonyl group. This is a 2+2 cycloaddition using the naming system we briefly discussed back in the Diels-Alder chapter. This gives us this 4-membered ring intermediate, which is called an oxyphosphatane. So you might be right to squint your eyes at that. There's quite a bit of ring strain in an intermediate like this, so this ring is prone to falling apart. This step is sometimes known as fragmentation, to give our new carbon-carbon double bond and triphenylphosphine oxide as a byproduct. So making ylids, how do we make them? Well, you start from haloalkanes, like 1, 2, 3, 4, 5. This is bromopentane. If I wanted to turn this into a 5-carbon Wittig reagent, I would treat it first with triphenylphosphine. So triphenylphosphine, that large phosphorus atom, is a very good nucleophile, which will cause an SN2 reaction to displace the halogen. This gives us this charged phosphorus intermediate, and due to that charge there, this carbon is quite a bit more acidic than usual. In fact, the pK of this proton is somewhere around 35. So in a second step, we can simply add a base that is strong enough to remove that proton. The textbook favors organometallic reagents like butyllithium. Here I've used sodium hydride. It doesn't really matter as long as the base is sufficiently strong. So remove that proton, generating the carbanion here, which is then stabilized by resonance with the adjacent phosphorus atom. Remember that phosphorus is allowed to exceed its octet, being that it is not a third period element. We can also make some Wittig reagents which we'll call stabilized Wittig reagents. These are stabilized because they're conjugated with other groups and they have additional resonance forms. So for example, one stabilized Wittig reagent would be this one, where the carbanion is adjacent to a phenyl ring. There's extra resonance there. Or we could put the carbanion next to an electron withdrawing group like an ester or some other carbonyl group. Ketones or aldehydes also work here. There's also a specialized type of Wittig reagent that's called a Horner-Wadsworth-Emmons reagent. This is a stabilized carbanion. This carbanion has resonance both with the carbonyl group on the right of the ester and of the phosphonate ester on the left. It's quite stable. The advantage of these types of reagents is that after the Wittig reaction happens, after that cycloaddition and fragmentation, it tends to give products which are soluble in water and therefore very easy to remove from your reaction mixture. So why did this earn George Wittig the Nobel Prize? Well, in one word, it's the stereoselectivity of this reaction. So if I start with a compound like this, so a ketone with two different groups on the left and the right, then when I make an alkene, I'm going to be able to get two different stereoisomers. On one hand, I'm going to show this reaction here with 1, 2, 3, 4 butyl triphenylphosphine ylide. This is non-stabilized. In the other case, I'm going to show a reaction with a stabilized ylide. And what we're going to see, and what George Wittig studied, was that if we do this reaction with a non-stabilized ylide, we're going to favor the formation of the less stable alkene. Now, we have to be careful. The book says that this always forms the Z-alkene. It does not always form the Z-alkene. Often we would name this as Z. Remember that E and Z has to do with assignment of priority, and priority assignment has absolutely nothing to do with how bulky a group is or how stable the alkene is. The opposite is true if we have a stabilized ylide. So here we're going to get the more stable alkene. And again, it's often but not always named as the E isomer. Okay, so with these rules, can we draw the products of different Wittig reactions? I'm going to give you these three carbonyl groups, 2 ketones and an aldehyde, and we're going to treat them with these 3 Wittig reagents. What I'd like you to do here is use the rules about which alkene we get to draw the products of each of these 3 reactions. Pause the video here, come back when you're done. All right, so what are we going to do here? Step 1, the question we need to answer is this a stabilized or is it not a stabilized ylide? The second question is, does that mean we get the more or the less stable alkene? And then the third step is to draw the alkene we've decided we need. So in our first case, this is not a stabilized Wittig reagent. Notice there's a phenyl group here, but it's not conjugated with where our carbanion is, so don't let that fool you. In this case, we would get the less stable of the two alkenes, so the phenyl group and the cyclopentane ring would be on the same side. Our second example is also not a stabilized ylide, so again, we would get the less stable of the two alkenes. Here the ethyl group and the phenyl group would be cis to one another. The third example is stabilized. This is an example of a Horner-Wadsworth-Emmons reagent, and this will get us the more stable alkene. So in this case, the ester will tend to be away from the longer alkyl chain. That's it for the Wittig reaction. So let's do a little more practice here. What I'd like you to do now is show me how to make a particular product via the Wittig reaction. So the first compound I'm going to ask you to make is this one. This is octyl methoxycinnamate. It is an ingredient in sunscreen commonly made by Wittig reactions. The second one is this compound here. This is called leukotriene A methyl ester. So this is a bioactive compound. Now I want you to do this in two steps. For the first step, I want you to show me how to make this double bond via a Wittig reaction, the one that's adjacent to the epoxide. For the second step, I want you to show me how to make this double bond via a Wittig reaction. So that's the one that's going to be next at the cis double bond lower down on the chain. And finally, the Wittig reaction is very useful for a reaction or a process known as chain homologation. In this process, we take an aldehyde like this and treat it with a Wittig reagent to get an enol ether. So this is the ether of an enol. I've shown it here. For the first part of this, pick the Wittig reagent that you would use to do this reaction. After we get the enol ether, we can treat it with H3O+ to give an aldehyde, like so. We're going to lose methanol in this step. For the second part, I'd like you to show a mechanism of this process. I'm not going to be reviewing these. Instead, if you have questions about how these work, this would be an excellent question to discuss in class. That's it for the Wittig reaction. In the next video, we'll talk about Baeyer-Villiger oxidation.